I just hit the record button. Let's get started. Last lecture. It makes me a little sad. I really enjoyed interacting with you guys, both classes and my lab. It's been a very interesting semester. I enjoyed your company. I think I like who you are, and imparting whatever I know about chemistry and molecules to you guys. And I hope we were successful to some extent. So please do your evaluation, course rating, okay, if you don't mind. I don't need it for my academic career or my promotion or anything. I'm just curious because I need the feedback to see where I can improve myself if I'm continuing to teach. I think fall is going to be interesting. I think for the lab, fall is going to be probably hybrid, but for the CHEM8 classes, it's going to be pretty much the same way. I don't think I'm going to go into the lecture hall. I might get a better camera, and I don't know what else I can do to make things more interesting. Maybe I can do some face painting so that it's more interesting. You know, you might get a kick out of maybe I'll shave off one half of my head and the other half will remain. Okay.
I just wanted to chime in really quick and let you know, I don't know if the other students are having this issue as well, but the link on my Canvas to do the review of the course isn't working. So I don't know if anyone else is having that problem, but
I am too.
Really?
I tried last week too and it wouldn't work, but it could just be like me. I could email like some tech support or something.
My thing's doing the same thing, Professor. Like I go to click on the rating link and it just stays on the same page. It doesn't take me to another page.
Mine does the same thing. It said it expired May 5th.
It says it's expired May 5th. Ah, shoot. Then I screwed up. It's too late. Sorry. Yeah, I don't know why I had set it up on May 5th. This was the first time I was messing with it. I'll see if I can extend it. I'll talk to the tech people and see if I can extend it. If I can extend it, I'll send you guys another announcement. Okay. You can email me. Maybe you can you guys do me a favor? Can you guys email me if you have time and if you feel like what you think about about the course? Sure. The first 1/3 was pretty much like regular course, and then the pandemic happened, and then it became online. So maybe you can give me your candid opinion. If you feel like you can do that, whoever wants to do it, you can post it on. I don't mind. You can post it on Canvas too, or if you want to create a fake Google account and send it from there, that's fine too. Okay. All right. Let's talk about some chemistry. Okay. You will get the video recording and you will get the pictures of the board, so that should help. I'm sorry, I'm having some problems even at home and here. Whenever I'm on Zoom, everything else goes down the hill, because I don't know if it is because like a lot more people are using Zoom, and if that's affecting their performance, that could be a possibility. All right, we kind of running behind. So I'm going to just give you a glimpse of what carbonyl chemistry is all about, okay? And I'm going to condense probably 4 lectures into one, less than one. So this is all about, I push the record button, yes. Carbonyl chemistry. What's a carbonyl? Carbonyl is a carbon and a double bonded oxygen. That's carbonyl, okay? So let me put it in red, because if I change the color within this group, it's going to be really difficult for me to keep changing. So the red part, carbon double bonded oxygen, that's called a carbonyl, okay? Carbonyl, this is carbonyl. This guy is called a carbonyl group. And let me ask you a question. Okay, I picked up the wrong color. I'm going to draw an arrow with pointing at the carbon. what am I going to ask you about with the green arrow? You know the question.
Hybridization.
Hybridization. What's the hybridization of the carbon?
sp2.
Excellent. Okay, if that's the case, what's the geometry? What's the geometry around, including here, this point, this point, this point, and this point? 1, 2, 3, 4. The 4 points, the double bond, there is nothing on the double bond on this end other than the 2 lone pairs. Remember that this guy has 2 lone pairs. So the lone pairs, we kind of ignored the lone pairs. The lone pairs, the oxygen, the carbon, and whatever is here, let's say hydrogen or carbon. So point 1, 1, 2, 3, and 4. What's that shape? You know the answer.
Planar.
Planar, okay? It's absolutely planar. What's the angle here? Any of these angles, approximately? 90, 120, or 109.5, or 180?
120.
120.
Very good. sp2, that means 120. Okay. Okay, so this is a carbonyl compound, and there can be, the way we teach, the way I teach, I usually talk about 7 carbonyl compounds. Okay, so what we're going to do is we're going to keep the left side of the carbonyl compound pretty much the same. Okay, so on this end there will be something. Okay, there will be some group, and that group will be either made out of hydrogen or it's going to be made out of something carbon. Okay? So the left side can be hydrogen or carbon for any of these 7 molecules. So we're going to talk about 7 molecules. Hopefully we can complete it. I'm just going to give you like a rough idea about some of the reactions, their properties, and so on and so forth. Okay? So the left side of the carbonyl can be hydrogen or carbon for any of these 7 molecules. The right side is a little interesting. The right side can be, let me put it in a different color. The right side can be different things. If the right side happens to be a hydrogen, it's going to be of one kind of molecule, okay? If the right side is a carbon and the left side is also a carbon, this is left, this is left, so both sides carbon, that's going to be another kind of a compound, okay? We'll talk about that. We're going to classify that. If the right side happens to be a halogen, okay, X is a halogen, then those guys are called something else. The right side could be an oxygen attached to a hydrogen, then that's another type of a molecule. The right side could be an oxygen connected to not a hydrogen, but something with a carbon. That's another type of molecule. Then the right side could be you know what? I did a little screw up. Let me just change from here. I need to insert some other molecule here, so I forgot to do that. Let's do that. So the right side could be hydrogen or carbon with another carbon on the left side. Those two are of special kind of molecules. The right side could be a halogen. The right side could be an oxygen connected to another carbonyl. It's a weird looking molecule. Another carbonyl, and down here, something else. Another box, and that this end could be, when I draw the molecules, things will become more clear. So at this point, you might be a little confused. Once we draw the molecule, it'll become much more clear. So just imagine that this part could be an oxygen and a carbonyl and then something else. Okay, we'll talk about that in a second. That's another kind of a molecule. This guy could be an oxygen with a plain hydrogen. That's another molecule. The right side could be an oxygen connected with not a hydrogen but a carbon. Something alkyl, something with a carbon. That's another type of a molecule. And finally, we are coming to an end. The right side could be something made out of nitrogen. Nitrogen connected with whatever else. We will talk about that in a second. It could be a hydrogen or carbon, and the other side could be a hydrogen and a carbon. So these are the 7 different compounds. Okay. Type 1, this is compound type 1, this is compound type 2, this is type 3, this is type 4, this is 5, this is 6, and this is 7. These 2 compounds are of one type, one kind, okay? These guys are called aldehydes. These guys are called aldehydes. I'll draw some example on the right side so that it kind of makes sense to you, okay? So that this is getting pretty complicated so that you can connect the dots. When you have a carbon, carbonyl, carbon, something like that, those compounds are called ketones. Okay? And these 2 molecules make one kind of molecules. They undergo specific reactions. We'll try to give you a glimpse of that. Okay, so these 2 guys are of one kind. They're very similar in their behavior, aldehydes and ketones. I'm going to start talking about the middle of the 7 compounds, which is number 5. Number 5. And these 5 compounds, 1, 2, 3, 4, 5, they're 3, 4, 5, 6, 7. You can call them 1, 2, 3, 4, 5. They're another kind. These guys behave in a specific way, okay? And I'm going to start naming the middle guy first. The middle compound is called carboxylic acid. Carboxylic acid. CAR, if you cannot read it, if the screen is too blurry, what's happening here? Christina, okay, I'm going to decline. Somebody probably accidentally hit some button. Okay. CARBOXYLIC, carboxylic, YLIC, car, driving automobile, box, check in the box, Y, and lic, LIC, acid. Okay, carboxylic acid, sometimes it's just called an acid. Okay, that's a carboxylic acid. This is an ester. The next guy, number 6. Number 6 is an ester. ESTER. When you have hydrogen or carbon on this side, C double bond oxygen, O, and then something with a carbon. Okay, I'm going to draw examples and make sure that you understand which one is what kind of molecule actually they are. I'm going to draw them in one color so that you're not confused. That's a carboxylic acid. This is an ester. And these guys, when you have a nitrogen on this end, on the right end of the carbonyl, those molecules are called amides. They're called amide. These guys, these complicated looking molecules with two carbonyls, hydrogen, carbonyl, oxygen, carbonyl, another hydrogen. So it's kind of a symmetrical molecule. Two carbonyls, oxygen, and two hydrogens or two methyls or whatever, two benzene rings. These guys are called anhydrides. These guys are called black. Let's use the black color. These guys are called NaN hydride. Hydride. Anhydride, like no hydride. That means less hydride. Hydro means water. That means they actually come from taking two carboxylic acids and sucking out a molecule of water, and they become anhydride. Okay, that's how you put two carboxylic acids. The hydroxy groups are kind of pointing at each other. You take one OH and one hydrogen, and you kind of suck that water out. They connect together and form an anhydride. Once I draw them, I think it'll make more sense. These guys are called acid halides. These guys are called acid halides. Okay? Let's draw the compounds. I'm going to kind of fill them up over here. I know that the camera only goes up to this line approximately, so I'll try not to cross the line of control. Okay, I'm going to draw an aldehyde, not molecule type 1. So an aldehyde looks like this. Let's draw the carbonyl part in red. Maybe a little bit bigger so that you guys can see it better. Okay, I'm just drawing some examples. The right side for an aldehyde, it has to be a hydrogen. The left side, who cares? It could be a hydrogen or a carbon. Let's put a carbon. Okay, and let's put 3 hydrogens. This is an aldehyde, type 1. Okay, that's an aldehyde. What would ketone be looking like? Ketone must have, the bottom line is for ketone, you cannot have hydrogens at each end. It has to be carbon. That's a ketone. So this is going to be a ketone. Carbon, oxygen, and both ends, let's put something simple, 2 methyl groups. Okay, this is type 2, and this is a ketone. This is the ketone, you smell it when you pass by a barber shop or a shop, a saloon where they're doing nails. What is that compound called?
Acetone.
Thank you. Who is this, Laura? L?
Yeah, that's me.
Okay, it's acetone. This is called this is acetone. You can also use acetone for doing dishes. We do acetone. We use acetone in our labs, research and teaching, to do the dishes. Okay, that's an aldehyde. That's a ketone. Let's draw carboxylic acid. I love carboxylic acids. Let's draw carboxylic acid off of a benzene ring. This side can be a benzene ring. It can be methane. It can be like 10 carbons. It can be 5,000 carbons. It can be a cyclic carbon, whatever. It can be a naphthalene, 2 benzene rings stuck together, 10 benzene rings stuck together. It doesn't matter. Okay, so let's draw a benzene ring. Let's do a little review. 1, 2, 30. I think we're okay. How many pi electrons in this molecule? How many pi electrons? I'm not asking you to do any funky business. No calculations, no math. Count the number of pi electrons. How many pi electrons are there in this molecule? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
6.
6. That's it? Only 6? Yeah, 6 is the right number. Is it aromatic?
Yes.
Yes.
Thank you. So this is a carboxylic acid. This is number 5. Compound type number 5. That's a carboxylic acid. So what does carboxylic acid have to have? It has to have the carbonyl. See, that's that red guy. The red carbonyl is common through the 7 compounds. They must have the carbonyl to be in the carbonyl chapter in the book. Okay, carbonyl, then whatever else, depending upon tail and the shape of the body and the head, you call them different things. Aldehyde has 1 hydrogen and a carbon or hydrogen. Ketone, you cannot have hydrogen, it has to be carbon. Acid will be having something like this, and on this side it has to be a hydrogen or a carbon. There can be another carboxylic acid. Let's, if we have room, I'll draw it. Okay, so that's a carboxylic acid. Let's draw an acid halide. Let's draw an acid halide that's made from this carboxylic acid. Let's make this guy's the chloro version of the acid halide. How would that guy look like? Benzene ring, it's constant. Carbonyl, that's constant. For it to be an acid halide, on the right side, it cannot have the OH. It cannot have the OH, but it has to have a halogen. So let's take a halogen. That's it. This is an acid halide. It's an acid chloride. Type 3. We don't have any room to draw the anhydride. I'm going to draw the anhydride up there. Okay, an ester. I'm going to draw the ester based on a different molecule. Okay, just to give you a glimpse. The ester I'm going to draw on the left side. I don't want a benzene ring. In this time, I'm going to put a methyl group here. So the ester comes from the acid. So it probably was an acid to begin with. I'm going to draw the acid first, and then I'm going to convert it into an ester. So this acid is called ethanoic acid because it came from the 2-carbon alkane. I'm not going to teach you guys the names. It's too late. No time to learn the name of these compounds. I'm going to spare you guys from learning the names. But just in case you are curious, the formal name, like an Indian boy has or girl always have 2 names. That confuses the heck out of everyone in the Western world. Like our son is called Buju at home. It's kind of like a little name, like, it could rhyme with some sound. Maybe when he was born, maybe there was a bird that was chirping and then you call it like cuckoo or something, Maybe his son will be named Cuckoo. So that's the informal name. Then they have a formal name. He goes by Neil, so which confuses people because sometimes they think we have 2 children, 2 sons. Like, where is your other son? I'm like, he's our only son. Why are you calling him a different name? Like, well, it's too complicated. So its informal name is acetic acid. Formal name, it's called ethanoic acid in school. It has a very typical sour taste that you taste in something. And there is a word that describes it even more informal, okay? Then in its village, people call him by that. It's a V word. And when you open a bag of chips, you can taste it. What is it? What am I talking about?
Vinegar.
Vinegar. It's vinegar. Acetic acid is vinegar. It's ethanoic acid. So, but that's not what we wanted to talk about. I didn't want to talk about the acid. I want to show you an example of an ester. So ester cannot have that H. So I'm going to remove that H. Let's put something else. What's our go-to alkyl group? Methyl. The moment you replace the hydrogen with something carbon, its property changes completely because it's not a carboxylic acid anymore. The acidic proton is gone. It's got a carbon. It's much more stable. It cannot produce a proton. It doesn't behave like an acid. Now it's a pretty good smelling, nice molecule. This is called methyl acetate. Oftentimes, the fragrances, some of the compounds, like banana oil, what other compounds? Acetaminophen, no, acetaminophen is a wrong answer. Wrong. Many perfumes have esters as contributing to the scent, to the smell of the combo mixture. Oftentimes, you should realize that the perfumes are a mixture of different fragrances. It's not just one compound. Okay, so this is an ester. This is an ester. This is compound number 6. It's this guy. I am hoping that you guys can still see the bottom of it, because I think when we did the experiment, it was still covering it. If you cannot, we'll figure it out. An amide will be carbonyl. Left side, I told you that it can be a hydrogen or a carbon. Let's put a hydrogen and see what happens. What does it look like? So this amide came from this acid. That's not what I'm going to leave it as, but it came from this particular acid. This is the atom of carboxylic acids. You cannot get a smaller carboxylic acid than that, because in order for it to be an acid, see, this is minimum, like what you have to have to be a carboxylic acid. You must have the carbon, you must have a double bonded oxygen. So you must have the carbon double bonded oxygen, the carbonyl group. You must have an oxygen, you must have a hydrogen, because this is crucial for it to behave like an acid. So C, double bond oxygen, and OH, that gives you the carboxylic acid features, the performance of a carboxylic acid. It lets you pop it off and protonate something, and you become O-, okay? That's why I'm a carboxylic acid if I have a carbonyl and an OH. What's the smallest thing you can stick to a carboxylic acid on the left side? Left side is open game. Hydrogen, carbon, anything. Anything goes. No oxygen, no nitrogen, no sulfur, no phosphorus, nothing funny like that. As long as it's a hydrocarbon something, like a hydrogen or carbon on the left side, we are game. It's good. It goes, it flies. Okay? So that's the smallest hydrogen. This acid, the nickname, its mother calls him formic acid. Okay? And the formal name will be methanoic acid, because it came from one carbon great grandfather, which was methane. Okay, methane, and then it started oxidation, getting oxidation, and then eventually it became formic acid. Formic acid is something that one of the small insects, when they bite you, they inject you with a little bit of formic acid. What insect am I talking about?
I'm gonna guess and say a bee. Oh, you said bite, not sting.
It kind of stings. It bites. I have been bitten by that insect.
Mosquito?
An
ant?
Ant. When an ant bites you, it injects you with a little dose of formic acid. Okay, that's called formic acid. So that would be the formic acid. So that would be type 5. Okay, but we are trying to have an example of an amide. What does an amide have to have? It cannot have an oxygen. So let's erase it. It cannot have that hydrogen. It cannot have that oxygen. It has to have a nitrogen there. How many other things the nitrogen must be attached to? 2 other things. Remember, nitrogen is trivalent with a lone pair. So the nitrogen must have 2 other things attached. What are the 2 smallest things you can attach there? Hydrogen.
Hydrogen.
Let's put some hydrogens. Okay. This guy is an amide. This is type 7. We missed drawing an anhydride. Let's draw the anhydride up here because I think we have room here. Let's draw carbonyl. Let's draw carbonyl. On the left side, since there is a little room, let's stick a hydrogen as before. Okay, hydrogen. Then what does that strange looking anhydride have to have? Well, it has to have an oxygen after the carbonyl. Okay, let's put an oxygen. Oxygen. Then what else? Another carbonyl. Another carbonyl. Okay, another carbonyl. And what should be on the other side of the carbonyl? A hydrogen or a carbon. Since this side has a hydrogen, let's put another hydrogen on the other side. Okay, this is type 4. That's an anhydride. Where did it come from? If you take 2 formic acids and remove a molecule of water, somehow or the other, you get formic anhydride. Okay, so this is just the laundry list of the 7 different types of compounds. The bottom line is you must have a carbonyl in the middle. You can have a hydrogen or a carbon on the left. And on the right side, you can have different things. Okay, let's use the purple color. That's one thing. Hydrogen. This is thing number 2, carbon. Then you can have a halogen. Then it's an acid halide. Then you can have oxygen with a carbonyl and something else, a hydrogen or a carbon, preferably the same thing that's on the left side, like that guy. That's an anhydride. Then you can have a carboxylic acid. Then you can have an ester. Then you can have an amide. Now, as far as molecules in our living system, in plants, in animals, in like unicellular compounds, in living system, whatever compounds you're talking about, usually nature uses either an ester or an amide. I'm just going to say nature. Nature uses amides and esters because they are most stable. These 2 guys, good luck. They're very unstable. Acid halides and anhydrides are terribly unstable. They're actually, we manipulate these compounds to get to the bottom of the chain. Okay, we actually get there. Aldehydes and ketones are pretty much everywhere. We also have some of our compounds in our living system. They're aldehydes and ketones. We also have alcohols and amines in our living system. So whenever we are making a drug, a medicine, we're trying to invent a medicine like Alzheimer's drug or cancer drug or painkiller or whatever, metabolic disorder drug, insulin replacement or something, or some kind of neurodegenerative disease drug, not necessarily Alzheimer's disease. Usually the molecules are going to be either an amide or an ester, or could be something else. Could be an amine, could be an alcohol, not going to be an anhydride, it's not going to be an acid halide, okay? So let's take a quick look. This is pretty much like laundry list. So you guys have to kind of memorize this material. So I'm going to take a picture. I have a different phone, not necessarily a new phone, but it's better. It's the reject from my wife. She got a new iPhone, so I got her old iPhone, and it's pink. I'm really proud of my phone. I used to not like the pink color, but right now, can't afford to buy another phone. Okay, I'm going to upload the picture eventually. Any questions so far? Carbonyl. These are the carbonyl molecules. There are 2 classes of carbonyl molecules. We're going to talk about that as quickly as we can, maybe 15 minutes on this, 15 minutes on that, and that will pretty much bring to the end of our semester. Aldehydes, ketones, carboxylic acids, acid halides, anhydrides, esters, and amides. Okay, nothing much to discuss. We're going to probably need more discussion and explanation in the next set of writing on the board. Okay, do you have any burning question right now? If you don't, then I'm going to erase and keep going. Okay. Let's erase. So what kind of reactions do these compounds undergo? There is no point talking about naming of these molecules. You know, I just gave you a little bit of like glimpse of naming an acid, but let's not worry about it. It just, we have to compromise. At this point, I have to compromise. We have to compromise on the extent of our learning. As long as you have an idea like what carbonyl compounds are, I'm going to draw you guys. I think it's going to just to like create some excitement. I'm going to show you like a couple of 3 molecules. They're all painkillers. They're eaten taken during the time of fever or headache or leg pain or inflammation. Like I took some ibuprofen, Advil. So I'm going to draw those 3 compounds. Now, after going through this class, after going through this course, I think it'll make sense to you. You will be able to understand, that's how Tylenol looks like. That's how Advil looks like. That's how aspirin looks like. It'll really make sense to you. And I think that should be a happy feeling. Okay. So now, what I'm going to do is I'm going to show you like what happens to these molecules. How do these compounds react? What do they react with? Okay. And I'm going to keep it simple as possible. Carbonyl, okay? And then let's say on the left side, you have something. You have a hydrogen or a carbon, okay? On the right side, you have something else, whatever that something else is. Okay, it could be a hydrogen, it could be a methyl group, it could be an ethyl group, it could be a cyclopropyl group, it could be who knows what. It could be a benzene ring, it could be a chlorine, it could be a bromine, it could be an OH, it could be an O and then a methyl group, it could be a nitrogen. So depending upon what you have on the right side, the molecule will get its identity. We're going to call it an aldehyde, we're going to call it a ketone, blah, blah, blah. Okay, let me just show you what happens to the carbonyl molecule. When you look at this bond, I don't have a lot of time to go over it. Let me just redraw this carbonyl in maybe a little more clean. Nice carbon, oxygen, 2 lone pairs, and let's say this is the green bond is the pi bond. If you look at the molecule, think about it like the Death Star. Where is the weakest point? Which part of this whole molecule, the carbonyl molecule, is begging for some intervention or some attack that it can break up? Which bond in this molecule? This bond, that bond, or this bond? This is the pi bond. Which bond is most likely or most vulnerable to attack?
Pi bond.
Pi bond, the green pi bond. If the green pi bond breaks, the pi bond can break and move on top of the oxygen, or the pi bond can break and move on top of the carbon. Which way it's likely to move? Should it move on top of the oxygen, or should it move down to the carbon? How should you should be able to figure that out by now. Depending upon electronegativity of oxygen and carbon. Who wants electron density more? Who is more greedy?
Carbon.
Who is more electronegative, carbon or oxygen? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Does electronegativity increase left to right or right to left?
Left to right.
Left to right. So oxygen is more electronegative. Carbon is 2.5, oxygen is 3.5. Almost a difference of 1 unit. So if the pi bond is breaking up, should the electrons move down here or up there?
Up towards the oxygen.
Up toward the oxygen. So the species that can make it happen, that can take advantage of this weakness in this fort, the place where the burglars are going to break into the house. That's a pretty terrible metaphor. I didn't say that. Okay. A nucleophile comes in with a lone pair. It attacks, and the pi bond goes up. That's how the first reaction with a carbonyl chemistry, carbonyl molecule, that's how it happens. That's how all hell breaks loose, starts to break loose. Once that happens, what does it look like? Now the pi bond, the pi bond is up there, okay? The left side is still there. Hydrogen or carbon. Right side, whatever you have, I don't know what you have. It could be a hydrogen, a methyl, it could be a chlorine, it could be an OH, it could be an OCH3, it could be a nitrogen with something, or that whole anhydride bulk, OCO something else, okay? So that, and the nucleophile. The nucleophile is also in, okay? This is an intermediate. This is an intermediate, and this guy, at this point, cannot be neutral. It is negatively charged. You should be able to figure that out by now. That should be your take-home message. That should be your takeaway wisdom from this course. Once the nucleophile attacks the carbon, the pi bond is up on top of it. The oxygen has 1, 2, 3, 4, 5, 6, 7 electrons. Oxygen is born with 6 electrons in its valence shell, so it's got 1 extra electron. Therefore, it is negatively charged. It's an anion. Now, remember I told you that the aldehydes and the ketones are one group, and everything else is the second group. The acid halide, anhydride, carboxylic acid, ester, and amide. Those 5 compounds and the 2 compounds, if we group them, one group will do the reaction in one way. They will both undergo the first part the same way. Nucleophile will come and attack. Carbonyl will get pushed up. The pi bond will be on top of the oxygen. Oxygen will become negative, and the nucleophile is stuck there in the middle of the carbon, and everybody is hanging on to it. Now, depending upon what you have here, this is very important. This part is very important. Depending upon what you have here, if you have an aldehyde or a ketone, hydrogen or a methyl, then the reaction will go in one way. Or if you have one of those 5 things, halogen or that big tail from an anhydride, or OH or OCH3 or NH2 or N something, then that reaction is going to go in a different way. Now, the question is, good living group? That's the question. If it is a good living group, or if it is a terrible, it's a sucky, bad, horrible living group, that's the question. If it is a good living group, the reaction will go in a completely different way than when it's a bad living group. So let's assume we're going to use 2 different colors. Let's use red for good living group, good Lg, okay, and black proud, bad Lg. Okay, when it's a good living group, it's going to go in a certain way. What will happen? When it's a good living group, the bond will kick back. It'll want to be a carbonyl again. Okay, how did carbonyl get its pi bond back? That could be the name of a story. The carbonyl got its pi bond back by kicking out the living group. So that's what is going to happen. Boom and boom. What will the product look like? Well, the carbonyl has regenerated. Let's pretend that the green bond came down. It'll probably make more sense to you. Now on the right hand side, this dude is gone. This living group is gone. Because it's a good living group, it's gone. Okay, it's out. It's like that previous story of nucleophilic substitution reactions. That guy is gone. Okay, what's in there? The nucleophile is in there. Okay, on the left side, you haven't messed with the left side. It's still a hydrogen or a carbon. Whatever it is, it's going to stay put. On the right side, that guy is gone. This guy is in. And whatever that guy was, it came out as a negatively charged species. It's a living group. So it has to be a decent living group. I'm going to tell you like what will happen to the other reaction. Then I'll give you the examples, like which compounds will undergo that route, the red route, and which compounds will undergo the black route. In this case, the black arrow way, it's not a good living group. It's a terrible, terrible living group. It doesn't want to be a negatively charged species. It hates to do that. In that case, this is not going to work. So if you don't do anything to this molecule, it'll be remaining as a tetrahedral. So this is sp2, and this is sp3. So this is called a tetrahedral intermediate. You don't have to know that. I'm not going to ask you that question, just for your understanding. I think it'll probably make more sense to you. This guy is an sp3 carbon. This guy is an sp2 carbon. This is flat. This is tetrahedral, 109.5-degree angle. If you don't do anything, and if you don't have a good living group, nothing is going to happen for eternity. Maybe humans will be extinct and dinosaurs will come back, or aliens will take over. It'll still be an O- with whatever here, nucleophile here, and the other group here. Okay, it's going to just hang in there forever. So what you need to do, you need to neutralize this guy by adding some proton. Where will the proton come from? Some acid. So dilute acid. Maybe a few drops of H plus, HCl or H2SO4 in water. So one normal HCl, one normal something. So H plus and water. Second step, this guy is going to grab that water, H plus. Let me just draw the H plus up here. The negative charge will grab the H plus and it will become an alcohol. It will become an alcohol. Let's say that green bond was used for doing that business. Dumb Siri. Okay, I'm going to shut this thing off. I'm still getting used to this iPhone. Super smart iPhone. Okay. The oxygen has picked up a proton. On the left side, you have carbon or hydrogen. On the right side, whatever the molecule was born with, it's still there because it's a bad living group. It can't come out. And the nucleophile is in. Okay, so from a carbonyl compound, you made a non-carbonyl compound, an alcohol. Okay, and the carbon in the center used to be flat and sp2. Now it's sp3. Okay, it's permanently changed. So it's kind of like metamorphosis. The pupa or larva became a butterfly. It actually looks like a butterfly. You can have a butterfly-looking molecule. You have a bunch of like aromatic groups. Okay, so the carbonyl compound transformed into something different. Now I'm going to ask you a question. This route and this route. Okay, let's call it the red route and the black route, or right route or the left route. The regenerated carbonyl with a good living group and the alcohol with a bad living group. Which one is a substitution reaction and which one is an addition reaction? Take a look at the molecules, reactions, and tell me which side is substitution. Answer that first. Which side is substitution, right or left?
Right.
The right is substitution.
Right.
Does everybody see that? Hopefully you can see that, because you're replacing this guy with a nucleophile. You're not replacing anything. So this is what kind of reaction? Elimination, substitution, or addition? The left reaction. Elimination, addition, or substitution? What's the right answer?
Addition.
And
Thank you. So this is addition and this is substitution. So both reactions are, this is called nucleophilic acyl. Acyl, I don't know why we use the word acyl. Think carbonyl when you read acyl, okay? Acyl means carbonyl. Nucleophilic acyl, acyl means carbonyl, okay? It's not exactly that, but just forget about it. So this is called, this reaction is called nucleophilic acyl substitution here. On the right side and addition on the left side. Okay, nucleophilic acyl addition for these guys and nucleophilic acyl substitution for these guys. Okay, now the question is which compounds will undergo what kind of reactions? Once we talk about that, it's about 15 minutes left. Once we talk about classify those class categories, then I'm going to give you guys a few examples and that will pretty much be it. Okay, let's take a look at, let's stare at the board for like 15 seconds. I was going to say 5 minutes. That's not going to work. Let me use my smartphone. You guys are okay with what you have seen so far? Nucleophile comes, attacks the carbonyl carbon, pushes the pi bond on top of the oxygen. The flatness is gone. It's not a flat land anymore. It's got depth now. It's got, finally the thin child is becoming healthy, as we used to say in India. Oh, your child is very healthy. That means she's saying, oh, she whatever. Okay, I don't want to get fired for using inappropriate language on the last class. On the left side, you have hydrogen or carbon. The nucleophile is in. Whatever is there, it could be, remember from the past, just what we drew and erased. Hydrogen, carbon, it could be a chlorine, it could be an oxygen, carbonyl, something else. It could be an oxygen and H, it could be an oxygen and R, like a OCH3, like an ester, or it could be something made out of nitrogen. Depending upon what you have there, the reaction can go substitution or the reaction can go addition. Substitution will happen when this guy is a very, iffy, vulnerable, like jittery, like unstable person. It wants to get stability by unhooking itself from that house. It wants to get out and feel good, even though it's not, it's kind of a wild world out there. Okay, it wants to be doing that. It wants to generate a negative charge and then explore the world. This is like, I don't want to, I'm comfortable in the house. I don't want to leave. Whoever comes in can stay with us. I'll share my room. And then whatever happens to that place, the oxygen, I don't care. Figure it out. How do you figure it out? You have to neutralize that negative charge. The only way you can neutralize a negative charge is by dropping a proton. You can add a proton at O minus or N minus or whatever minus will become OH, in this case, OH. So it becomes an alcohol. So two different types of reactions. Are we good? We have to keep moving, okay? I'm not going to take any questions. Let's move. It's being recorded, so no need to panic, okay? Now let's clean up the board and let's see which compound will undergo what kind of reaction. So carbonyl. I'm going to draw some specific molecule, okay? Let's say hydrogen. You know what? Let's put a methyl group on all of these compounds. Methyl group, and on the right side, you have a hydrogen, another compound, methyl, same methyl, and another methyl, okay? So if these reactions, if these guys undergo, this is an aldehyde, and this is a ketone. Okay, if they undergo a nucleophilic attack, for example, OH minus, okay, if it undergoes OH minus and it becomes this, OH minus is in, the hydrogen is out there, and I'm going to use the same nucleophile for all the compounds. OH minus attacks, okay? Carbon becomes O minus. There is a methyl group here, there is a methyl group here, and there is an OH minus here. OH minus is in as a nucleophile. Now let's draw the other compounds. Let's draw the carbonyl. I'm going to skip the anhydride. I'm just going to draw 3 compounds, okay? Because just to save time. So on the left side, let's say you have a methyl, methyl, methyl. On the right side, you have a chlorine. On the right side, you have, I'm going to make an ester, and on the right side, you have NH2, okay? So this is an acid halide. Time is ticking. This is an acid halide. Let's call it an acid chloride. I'll just call it the general name, acid halide. This guy is an ester, sweet smelling ester, E-S-T-E-R. That's an R. I know that my handwriting is getting bad. And this guy is an amide. I love teaching this section, the carbonyl chemistry. I just wished we had at least two more sections. Okay, so it's being hit by this nucleophile. The nucleophile comes and attacks and makes this species, and this reaction also undergoes the same type of reaction. Okay, I'm using the same nucleophile across the board so that you guys don't get confused. We are using the same nucleophile for all the compounds except for 2, carboxylic acids and the anhydrides. We just don't have enough room on the board. If I was using the whole board in a regular classroom setting, I would have used that. But we just have to compromise at this point. There's nothing we can do about it. O minus, O minus, O minus. Down here you have a halogen. On the right hand side for this molecule you have OCH3 for an ester, and for this guy you have the NH2 of the amide. And then the hydroxy, the nucleophile is in. That's the whole point. Okay. Now, these intermediates, tetrahedral intermediates, it looks like a hospital bed with the newborns sitting in their cribs. 5 cribs with 5 little babies. They look kind of cute. Don't you think so? Okay. All right. The question is this part, right? This is the questionable part. This is where the fate of the reaction is going to be depending. This guy, the right side, this guy, and this guy. Okay. So if they come out, assuming they're all wonderful living groups, if we can make that assumption, what comes out of here, okay, whatever reaction takes place next, whatever reaction happens here, whatever happens here, whatever happens here, whatever happens here, when that, if that reaction undergoes substitution, let's just analyze the living group. If this guy comes out as a living group, it'll look like NH2 minus. If this guy comes out as a living group, it'll come out as O CH3 minus. That's going to be the living group. If this guy comes out as a living group, it'll look like Cl minus. Cl minus, OCH3 minus, NH2 minus. In this case, it'll be a methyl minus. CH3 minus, and in this case, it's going to be a H minus. I wish we had more time to kind of connect it with acidity and basicity. We don't. So I'm just going to tell you that as far as the living group, so we are all talking about down here, along this line, we're talking about living group. Okay, that's a living group. That could be a living group. That could be a living group. That's a living group, and that's a living group. I'll tell you, does anybody want to make a guess like which one is the best living group and which ones are the worst living group? H minus, CH3 minus, chlorine minus, OCH3 minus. Think about methanol, lost its proton and became OCH3 minus. Ammonia lost its proton and became NH2 minus. Which one looks like the best? They're very happy. Octet is full, kind of roundish shape. You know, I feel like one of the inert atoms. I don't have any bag and baggage. I'm so happy. Which one looks like that? Any guess?
Chlorine?
Perfect. This is the best. This is the best living group. This is awesome. This is, I'm just going to say, this is awesome. This is okay. Okay? This guy is bad, but can happen. Push comes to shove, if you reflux it at 150 degrees for 3 days, it'll probably react. Maybe not 100%, it might react like 50% or whatever. It can happen. That reaction can be pushed if you really hit it with a hammer for like 24 hours. It can happen. H minus and CH3 minus, no matter what you do to them, they're not going to come out as H minus and CH3 minus. I can guarantee you that. Unless you do something outrageous, otherworldly. Okay? They are just not living groups. Let's call it, they're not living group. Okay. So they are not living groups, aldehydes and ketones. They don't have any living groups. These 7 compounds, acid halide, anhydride, we haven't talked about it, ester and amide, they have some living group, properties. Acid halides are the best, anhydrides are next best, acids and esters are so-so, and amides are pretty sucky. They're pretty bad, okay? Now you guys tell me, with the division in the middle, aldehydes and ketones are on the left side, acid halides, anhydrides, esters, acids, and amides are on the right side. So the 2 classes, class 1 and class 2. Which class, the left class or the right class, will undergo nucleophilic, listen carefully, nucleophilic, you can close your eyes, nucleophilic acyl substitution reactions? The right class or the left class? Substitution, which one?
Right class?
Fantastic, Christian. Because they have living groups of different strength. Awesome, okay, bad, but it's still a living group. So these reactions will be going this way. I'm going to use different colors so that it kind of stands out. Boom, 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 out, out. This will need heat. This reaction will need heat. So all these reactions are going to produce, it's really funny, all these reactions are going to produce the same product. It will all produce vinegar at the end of the day, with this living group as a byproduct, with methoxide as a byproduct. We can make methanol from here by treating it with water, and amide from here, you can make ammonia from here. This reaction is going to be very difficult, very, very difficult, very difficult. You might need a lot of things. These reactions, they're not going to behave like living groups. So you will have to add H plus and water. Unless you do that, this is not going to do anything. And when you add H plus, the negative charge is going to pick up the proton and make a completely different looking molecule. And that's going to look like, in this case, it's going to look like two methyl groups on two sides. In this case, one methyl and a hydroxy down here, one hydroxy, and this guy. And up here, it's going to look like this. The green proton has been picked up. So these two products are nucleophilic N acyl A addition. Nucleophilic acyl addition. On the right hand side, the reactions are going to be nucleophilic acyl substitution. Okay, nucleophilic acyl addition, nucleophilic acyl substitution. Unfortunately, we have to stop here. As much as I would like to continue and talk about stuff, what are the different reactions, what are the products called, blah, 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 we have to stop. We are already over time. Well, according to the computer, we have like 1 minute left. My clock is showing, oh, it's probably fast. So this is what happens. This is included in the final exam. And we're going to talk about it in the review. So what did we say about the review? Friday, 5 to 7, roughly. I'm going to send an invite for Zoom, and we're going to go from there. I don't think the Zoom problems that you guys are having, it has to do with maybe anything, but just in general, just having problems with Wi-Fi. We are having a lot of additional problems at home. Any questions so far? I'm going to take a picture of this board. Let me switch over to this camera. How many of you are there right now? 25. I think the number has dropped as always. So any questions? Did I miss something? You guys are hanging in there? If there is no other discussions or any questions or concerns, I really enjoyed, this was an interesting semester, but I enjoyed, spending time with you guys, sharing what I know with you, learning Zoom, relearning how to make videos and upload it on YouTube and share. I had done it in the past, but the knowledge kind of evaporated. it's kind of volatile. So, it was not a bad idea. I learned a lot. I learned that I can get more responses from you guys using this technique, modern technology. You're not as, even if you're shy, but you can probably write something on the chat and say something from your end, from your camera. So I think I'm seriously considering adding it to my teaching, otherwise traditional teaching technology. So hang in there, study, and we will see you guys, some of you guys, on Friday at 5. I'll send some announcements, and I will post the key on sometime in the next, I think, probably not today, maybe tomorrow. Somebody was saying something. Did I interrupt? Any questions, concerns, chit chat?
Thank you for the semester.
Thank you, Annabelle. I appreciate it. Thanks for hanging in there. Thanks for all of you guys.
You made the transition a little easier than a few other teachers.
Appreciate that. Appreciate that. If you guys can send me some write-up. I know that I screwed up with the deadline. I think I put 5th. I have no idea why I did that, like an idiot. If you guys can send me like a little write-up, maybe by email, I'll really appreciate it. Okay, whatever you have in your mind. And it's not going to go against your grade, I promise.
Or you didn't get a chance to make me sit in the back.
How are you?
Good. This is still hard, but I'm going to be there on the review on Friday.
Okay. All right. Anybody else? Hope to see you guys around afterwards. Hopefully things will open up. I mean, things are slowly opening up. I'm not sure how it's going to pan out, but I'm just keeping my fingers crossed. Like everybody else, I'm also tired of sitting at home and not being able to be
My
ourselves.
restaurant's super busy up in Shaver. Like, it's really busy lately.
Seriously?
Yeah, everyone's coming up and just getting takeout and then eating their pizza in the car.
Okay. That sounds like a good idea. Be safe. Continue to be safe, especially if you have like elder people living at home with gray hair like me. So don't make sure that their lives are safe. Okay. 16, down to 16. Thank you. I really appreciate it. And those of you who have written emails with some positive comments, I appreciate it. As I say, like, teaching is therapeutic. When I have a bad day or a sad day, usually after I hang out with you guys, I feel better. Probably that's why after 9 years in industry, I came to teach in academia. Maybe it was my destiny to be miserable and happy. That can happen. All right, Richard, thank you so much. I'm not an awesome professor, Saisha. You're lying. I don't know why you're kissing up to me. I'm just kidding. That was a joke. Okay, go away. Mind your own business. Go play with your dog, cat, harass your neighbor's dog, cat, whatever you want to do. Take care, okay? Be safe.
Have a good day.
Bye. See you around afterwards.